Picture the solar system for a second. It feels pretty predictable, right? We've got our planets in their lanes, our moons ticking like clockwork, and a rule book of physics that we've confidently relied on for generations. It's easy to feel like we've seen all the tricks our cosmic neighborhood has to offer. Hold that thought, because something else is happening right now that most people haven't fully processed yet. 6 astronomical units from where you're sitting, roughly 900 million kilometers out, drifting slowly through the constellation Gemini, a visitor from another star system is hemorrhaging water into space at a rate of 2,000 kilograms per second, every single second. That's 70 Olympic-sized swimming pools, every day, boiling off into the void from an object that shouldn't be doing this anymore. By every model we had before it arrived, by every equation built on decades of cometary science, 3I Atlas should be quiet by now. Dormant, winding down. The sun's warmth at this distance is less than 3% of what Earth receives. Classical physics says the party should be over. It isn't over. And that single fact, 2,000 kilograms of water vapor per second at 6 astronomical units in April 2026, is quietly dismantling something we thought we understood. To appreciate why this is so strange, you need to feel what 6 astronomical units actually means in your body. Not as a number, as a distance. Light travels at roughly 300,000 kilometers every second. From the surface of the sun to the Earth takes about 8 minutes. 6 astronomical units means the sun appears roughly 6 times farther away than it does from your backyard. If you stood on the surface of whatever is left of 3I Atlas's nucleus right now and looked back toward the inner solar system, the sun would be a brilliant but noticeably smaller point of light, still the brightest object in the sky, still warming you slightly, but reduced, diminished, like standing in a room and watching someone carry a candle to the far end of a cathedral. The light reaches you. You can see it. But the warmth? Barely. At this distance, water ice doesn't just reluctantly sublimate, it stops. Or it's supposed to. The energy budget simply doesn't support it at scale. Comets at 6 astronomical units are cold, dark, silent things. Jupiter itself orbits at about 5 astronomical units, and the comets we've watched in the outer solar system beyond Jupiter's orbit are typically inert. Rock and ice locked in their own frozen geology, waiting for a gravitational nudge to carry them sunward, where the real fireworks begin. 3I Atlas is not behaving like those comets. The data coming back from the European Space Agency's JUICE spacecraft, a mission whose primary purpose is studying Jupiter's icy moons, not chasing interstellar visitors, is extraordinary. The SWI spectrometer aboard JUICE recorded water vapor outgassing that would be impressive for a comet at Earth's orbit. At 6 astronomical units, it defies the framework. And the source isn't just the nucleus. That's the detail that keeps planetary scientists awake. The overwhelming majority of these emissions are directed strictly sunward, yes, but they're not all coming from a single point. They're distributed across the coma, the vast gas and dust envelope surrounding the nucleus, which has now spread over 5 million kilometers of space. 5 million kilometers of active ice, not a solid structure, a diffuse cloud, and somehow the particles within it are still sublimating, still erupting, still breathing. This is not a small revision. This is a fracture in the foundation. To understand the magnitude of what's being challenged here, let's go back to what we thought we knew about how comets work. Because that story is actually beautiful, and understanding it makes the anomaly so much more viscerally strange. Comets are time capsules. This is not a metaphor. They are literal physical records of the primordial solar system assembled from the same material that built the planets, frozen in the outer reaches of the system before the sun ignited or shortly after, preserved in the cold dark for billions of years. When one of them is perturbed by the gravity of Neptune or a passing star or the slow oscillation of the galactic plane, it begins a long fall inward. As it approaches the sun, the surface temperature climbs. First, carbon monoxide sublimates because it requires almost no heat. Then, carbon dioxide. Then, as the comet crosses the frost line somewhere around 3 astronomical units from the sun, water ice begins to turn directly to vapor. The classical model is elegant. Each volatile material has a sublimation temperature. Each temperature corresponds to a distance from the sun. Move the comet closer and you activate the next layer. Move it farther away and the comet shuts down in reverse order. Water, the last of the common volatiles to activate, is also the first to go quiet as the comet retreats. Past 3 astronomical units, maybe 3.5 astronomical units, if the comet is particularly active, water gassing drops dramatically. Past 5 astronomical units, it effectively ceases. This model isn't speculation. It's been confirmed by direct observation of dozens of comets over the past 50 years. It works beautifully for solar system objects. 3I Atlas came from somewhere else, and it brought different rules. The spectral data from JUICE hints at something that, when you sit with it, is genuinely unsettling. The sunward plumes, these columns of gas and dust directed almost perfectly toward the sun, may be the surface expressions of localized microexplosions happening beneath the nucleus's outer layer. Phase transitions of ice, not simple sublimation, where a solid gently becomes a gas, but sudden structural rearrangements happening inside the material as it slowly warms. Picture a thin crust of dust covering a layer of amorphous ice. Ice that formed at temperatures close to absolute zero in the interstellar medium, packed with energy like a compressed spring. As heat slowly penetrates the dust layer, the amorphous ice doesn't simply melt, it snaps. It reorganizes into crystalline form, and that reorganization releases energy, a burst of heat from within the material itself. This process is called exothermic crystallization, and we've seen hints of it in solar system comets before, but never at this scale, never sustained like this, and never distributed so widely across a coma 5 million kilometers in diameter. What 3I Atlas may be showing us is a reservoir of primordial interstellar ice, material that formed around another star, or possibly in the cold, dense molecular clouds between stars, that has never encountered enough heat to reorganize until now. It has been traveling through the void for potentially millions of years, carrying its chemical state like a letter sealed in an envelope that nobody has ever opened. We're opening it right now, in real time. And here's the open loop I want you to hold in the back of your mind as we continue, because we'll come back to it. if the activity can be sustained at 6 astronomical units by internal energy release rather than external solar heating, how long can it continue? And more profoundly, what is it actually made of? What specific chemical signature does this interstellar ice carry? And does it match anything we've seen before? Or is it something entirely new? The answer is still forming. Europa Clipper, the NASA mission currently en route toward Jupiter's ocean moon, is positioned to contribute additional observations. Hubble and JWST continue to monitor. TESS, built to find exoplanets by watching for tiny dips in starlight, is now watching 3I Atlas with the same patient precision it applies to stars light years away. These instruments are extraordinarily sensitive, and yet the chemical fingerprint we're looking for, the precise molecular composition of this interstellar visitor's volatiles, is still being decoded. So while we wait for that answer, let's ask a different question, one that reframes everything. What does it mean that 3I Atlas is here at all? Not why it's active, not what it's made of, but what it means cosmically that an object from another star system has passed through our solar system during the brief window when we had the instruments to detect it, track it through perihelion, and now interrogate it remotely with spacecraft that were already in the outer solar system doing something else. To feel the weight of this, you need to think about timescales. The universe is approximately 13.8 billion years old. Our sun has been burning for 4.5 billion years. Modern observational astronomy, the kind capable of detecting something like 3I Atlas, has existed for perhaps a few decades at the level of sensitivity required. The objects that pass through our solar system don't announce themselves. They don't slow down. They arrive from the darkness, fall through the inner system in weeks or months, and vanish back into the interstellar void on hyperbolic trajectories that will carry them away forever. We caught this one. The probability calculation here is staggering. The solar system is not a small target, but interstellar space is almost inconceivably empty. The average distance between stars in our galaxy is measured in light years. 1 light year is about 9.5 trillion kilometers. The stars are scattered across a volume so vast that even traveling at reasonable interstellar velocities, the chance of any given small body from another system threading through the habitable zone of our solar system during the centuries of human civilization, and further still, during the specific decade when we have the instruments to recognize it, image it, and dispatch spacecraft to study it, is not zero, but it is profoundly small. And yet, here we are. Some researchers think this points to a higher number density of interstellar objects than our models predicted. If we're seeing them now, regularly, 1I Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas, then the galaxy may be seeded with an extraordinary abundance of small bodies ejected from other planetary systems. Every star that forms planets also ejects material. The gravitational chaos of planet formation flings enormous quantities of debris outward. If nearly every stellar system does this, and they've been doing it for billions of years across hundreds of billions of stars, the sheer number of interstellar drifters crossing the galaxy becomes almost incomprehensible. In this picture, 3I Atlas isn't a once-in-a-billion-year freak. It's a message from a routine process happening everywhere, all the time, on scales that dwarf human comprehension. But the question of what it carries, the open loop, is still unresolved. Let's come back to the activity, because it forces a deeper question about the structure of the universe's chemistry. When we detect water vapor outgassing from 3I Atlas at 2,000 kilograms per second, 6 astronomical units from the Sun, we're detecting the behavior of a specific molecule, H2O, that formed in conditions very different from our own solar system. Water is not exotic. It's one of the most abundant molecules in the universe. Hydrogen and oxygen combine wherever the conditions allow, and the conditions allow it in many places. In molecular clouds, in the disks of gas and dust around young stars, in the cold mantles of interstellar dust grains. This object arrived carrying water. That's not surprising. What's surprising is the energy architecture of that water, the way it was stored, the way it's releasing. Consider what our Sun has to offer at 6 astronomical units. The solar irradiance, the energy per square meter arriving from the Sun, falls off with the square of the distance. At 1 astronomical unit, it's roughly 1,360 watts per square meter. At 6 astronomical units, it drops to about 38 watts per square meter. You can generate more energy from a standard household LED bulb than the Sun delivers to 1 square meter of 3I Atlas's surface right now. And yet something is powering a continuous, massive outgassing across 5 million kilometers of space. The distributed nature of the emission is the critical clue. If it were only the nucleus, a single dense body with some exotic composition or unusual albedo, you might be able to construct a model where surface features or unusually dark patches absorbed just enough heat. But the coma itself is active. Dispersed ice particles, scattered through a cloud wider than 4 times the distance between the Earth and the Moon, are sublimating. This means the energy isn't primarily coming from outside the material. It's coming from within. Exothermic crystallization is the leading candidate. But there's another possibility that's harder to dismiss the longer you think about it: radioactive decay. Short-lived radioactive isotopes, aluminum-26, iron-60, are produced in supernovae and in the winds of massive stars. They decay relatively quickly by cosmic standards, but in a freshly formed planetary system, they can heat the interiors of even small bodies significantly. If 3I Atlas formed early in its parent stellar system's history, near a source of short-lived isotopes, some of those isotopes may still be decaying at low levels, or the heat deposited during that early period may have created specific structural features: pre-sintered ice with different thermal properties, subsurface voids, layers of altered chemistry that allow it to sustain activity now. This isn't speculation for speculation's sake. Radioactive heating is a known driver of internal activity in solar system bodies. It's what makes the interiors of icy moons like Enceladus and Europa liquid. The same physics applies to any body rich in the right isotopes. And 3I Atlas has been traveling through interstellar space for we don't know how long. It could be millions of years. It could be hundreds of millions. The isotopes might be long gone, but the structural imprint they left could still be there, encoded in the architecture of the ice. We're reading a geological record written by physics we don't fully understand yet, in a language we're only beginning to decode. Now, pull back further, much further. Because 3. I-Atlas exists within a context so large that even the solar system, the Sun's entire gravitational domain stretching nearly 2 light-years to the Oort cloud, is a microscopic detail within it. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. It spans about 100,000 light-years. The disk is roughly 1,000 light-years thick in most places, and within that disk, stars are constantly forming, evolving, and dying, each one potentially ejecting comets, asteroids, planetesimals, and the debris of failed and successful planetary systems into the interstellar medium. This material drifts, it travels, it encounters gravitational fields, stellar winds, the diffuse radiation of the galaxy. Over billions of years, the Milky Way becomes a kind of slow, continuous exchange of planetary material, a cosmic metabolism in which no star is truly isolated. What 3I Atlas is, in this framing, is a metabolic product, a cell sloughed off from some other living part of the galaxy's body and delivered by chance or by the cold arithmetic of orbital mechanics to our doorstep. And, beyond the Milky Way, 2 trillion galaxies at current estimates, each performing the same processes, each exchanging material with itself, and, over cosmic time, occasionally with others. The Andromeda Galaxy is currently on a collision course with the Milky Way. 4 to 5 billion years from now, the 2 galaxies will begin to interpenetrate in a slow, largely star-missing gravitational dance, and the interstellar medium of both galaxies will mix. The comets, the asteroids, the raw chemical building blocks of both galactic civilizations, if there are any, will scatter into new and unpredictable orbits. The universe, at this scale, is not a collection of isolated islands. It's a continuous churning system in which everything is connected by gravity, radiation, and the slow drift of matter across unimaginable distances. 3I Atlas is a thread in that fabric, a tangible one we can actually study. Let's return to what the JUICE observations tell us and what they might mean for the future of this field. The fact that the SWI spectrometer can detect water vapor from an object at 6 astronomical units with the precision needed to measure outgassing rates is a triumph of instrumentation. But the more significant implication is what this detection demands of our theoretical framework. If 3I Atlas is extremely active yet not exotic, as the published characterization puts it, then we've been wrong about the baseline. We thought extreme activity at large heliocentric distances was rare, unusual, worthy of special explanation. But if an interstellar comet that appears in most ways unremarkable is sustaining this level of output at 6 astronomical units, then our definition of what's normal for comets at large distances needs to be rebuilt from scratch. It's not exotic, and yet it breaks our models. That tension is important. It means the models were wrong, not the object. And this matters enormously for how we think about the future. Cometary activity at large distances affects the composition of the interplanetary medium. It affects the delivery of volatiles to planetary surfaces. In our own solar system, the delivery of water to the early Earth, a question still actively debated, may have been partly accomplished by comets arriving from the outer solar system, perhaps even interstellar visitors that were active at distances where we didn't think they could be. The chemistry of life's origin is tangled up with the chemistry of cometary ice. If we've underestimated how far from the sun a comet can sustain water outgassing, we may have underestimated the role of cometary delivery in the history of Earth's water and, by extension, in the history of life itself. The open loop closes here, partially. The composition question, what specific molecules does 3I Atlas carry, what isotopic ratios, what molecular complexity, is the next chapter. Hubble's ultraviolet sensitivity, JWST's infrared precision, and the spectroscopic capabilities of ground-based observatories are all pointed at it. The full molecular inventory of this visitor is still being assembled, and somewhere in that inventory might be the first direct chemical evidence of how another stellar system's chemistry compares to ours. Not a theory, not a model, a measurement. That's an almost incomprehensible scientific opportunity, sitting 600 million miles away, slowly fading, slowly cooling, slowly moving outward toward a darkness it will not return from. Because that's the other thing you have to hold. This is temporary. The orbit is hyperbolic. 3I Atlas is not bound to our solar system. It came from somewhere else. It passed through, and it's leaving. The tail will fade. The coma will dissipate. The nucleus, whatever remains of it after the violence of perihelion passage, will cool and go dark as it retreats into the outer solar system and eventually into interstellar space again. In the centuries to come, it will be too faint for any instrument we currently possess. In the millennia to come, it will be beyond the sun's gravitational reach entirely. One day, far in the future, after you and everyone you know, and everyone their descendants will ever know is gone, 3I Atlas will be a cold, dark rock drifting between the stars again. It will carry the chemical memory of our sun's touch, the photons that struck it, the solar wind particles that embedded themselves in its outer layers during perihelion. In some small physical way, it will carry evidence that our solar system exists. It will be a message we sent without meaning to. And if, improbably, impossibly, something in some other star system happens to intercept it, if some other civilization in some other epoch of this galaxy's long life develops the instruments to study a cold interstellar object falling through their neighborhood, what would they find? The signature of our sun in its isotopic fingerprint, the chemical processing that our solar wind performed on its surface, a record that our star exists, that it shines, that it touches the things that pass through it. We are looking at 3I Atlas right now, and we are the universe looking at itself, briefly, through instruments we invented in the last century, on a planet that formed from the same exploded stars that built every comet in every galaxy, asking questions that may not be answered until long after we're gone. The SWI spectrometer aboard JUICE registered 2,000 kilograms of water vapor per second at 6 astronomical units in April 2026. That measurement exists. It's encoded in data transmitted back across hundreds of millions of kilometers, received by antennas built by human hands, processed by algorithms, written by human minds. It is one of the most intimate contacts we have ever made with material from another star system. And it told us something we didn't know, that comets can sustain themselves in ways we didn't think were possible, that the universe's chemistry is richer and stranger than our models assumed, and that the old idea of comets simply switching off as they retreat from the sun is not a law. It's a parochial assumption built on the limited sample of objects that happen to call our solar system home. The sample size just got bigger, and the implications are still unfolding. There are things happening right now at this exact moment in the constellation Gemini, 6 astronomical units away, involving ice that formed around another star, releasing water into interplanetary space, being watched by 3 of humanity's most powerful observatories simultaneously that we don't fully understand. That gap between what we observe and what we can explain is not a failure. It's the most alive edge in science. It's where understanding actually grows. Somewhere in that gap, in the fading tail of an object from another star system, something true about the universe is waiting to be found. If that thought stays with you, if the feeling that we are an infinitesimally small, but somehow genuinely observing part of a cosmos this vast stays with you, then stay with us. Subscribe, and be here when the next piece of the answer arrives.